But I want to start now because, I want to emphasize that this is where we've been heading all through the semester, right? Is the synthesis of motion in heaven and motion on earth, okay? And I'm going to do a couple of very simple experiments that really showed Newton what was going on as to the fundamental laws behind motion, okay? So I already gave you two laws. I'm going to do that again, but this time I'm going to do it more carefully, all right? So Newton actually came out with three laws of motion, all right? The three laws of motion, the first law of motion is basically the same as what Galileo came up with. Namely, if you have a body that's moving, or it's at rest, okay? And if it's moving in a straight line, it will continue to do that forever and ever unless there's an outside force acting on the body. Okay? So Newton improved this law to introduce this second phrase. Galileo said a body remains in state of rest or uniform motion in a straight line forever. That's Galileo's law. Now Newton added, unless it is compelled to change that state by an outside force acting on a body. And so basically he put himself in the position of having to define what is force, okay? And that really is the key, the first key to Newton's insight into the behavior of nature, okay? Now, force is a word that's familiar to everybody, right? In order to lift a huge weight, you have to exert a lot of force, right? Or in order to propel an object in a catapult very far, you have to exert a lot of force. But what is a force? What is the definition of force? And this is the very deep concept that Newton introduced. Namely, force is the agency needed to realize a change in the state of motion. It's sort of a rephrasing of this, okay? i.e., acceleration. Force is what is needed to cause acceleration. So up to this point that he said this, the meaning of force was very vague, okay? So now I'll do that experiment that I'm really after, is I will show you Newton's meaning of force. Why isn't the slide going on? Here we go. All right. So here I have, once again, this fan cart from before, right? Okay, and it's going to move on this so-called frictionless track. Can everybody see that? All right. And I'm going to turn on one speed, okay? And you got some acceleration, okay? And I can turn on second speed. So there's, if I apply more force, there is more acceleration. Second speed. So there's, if I apply more force, there is more acceleration. Okay? So I have a fan cart, right? Let's say I have this fan cart. I get acceleration depending on the force. I can apply more force and I get more acceleration, okay? That's pretty obvious. Okay. However, the second part of this law is not so obvious, and that's really the deep thinking of Newton, okay? So what he says is that, suppose, let me use the slow acceleration. Okay? Now, I'm going to use that same slow, but I'm going to increase the mass of this cart. Okay? There's the acceleration. Okay? So now, this gives Newton a more precise way to define force. Okay? He says, if you now take a massive object and apply the same force, you'll get less acceleration. Two concepts here. Increase the force, you get more acceleration. Acceleration is proportional to force. Okay? Second, I did that. Now, if the same force is applied to different objects of different mass, then the acceleration is different, and what makes that different is the property which Newton defined called mass. Okay? So the more the mass, the less the acceleration, because the more the resistance to change in velocity. Okay? So increased mass, acceleration decreases. Acceleration is proportional to 1 over mass. Now put these two together. Okay? Put these two together. Acceleration equals force divided by mass. A equals F over m. Or this is the famous Newton's second law of motion. If I flip it, I get F equals ma. This is what you learn as the first thing in physics course, that force equals ma. This is Newton's second law. Powerful law, okay? Now, turns out that this law, together with his law of gravitation, which we will derive next time, gave him everything he needed to figure out all the motion of all the planets, all the motion of everything on Earth that we've studied so far. Namely, I'll come back to this question. You can use F equals ma to understand this motion, horizontal motion. You can understand pendulum motion. You can understand spring motion. You can understand motion of all the planets going around in the heavens with the use of Newton's second law. So this is a very powerful law. He needed only one more law. And in fact, one of the poets said, Newton figured out the design of the universe in 2 lines. F equals ma is the first line. Okay. Or F equals ma, where a is acceleration. And remember that acceleration is a vector. Okay. And just like since acceleration is a vector, force is also a vector. And a vector, as you all know, has both direction and magnitude. And acceleration depends on force, but what makes the acceleration different for the same force is this unique property of the body, which Newton called the mass of the body. So the more the mass, the less the acceleration, which means the more the resistance to any change in velocity, because that means acceleration. Okay, so that's the meaning of mass. And that's the only meaning of mass that Newton used. Okay? All right. Now, to dwell on this concept of mass for a little bit, because of the fact that there's been a lot of confusion, mass is this unchangeable property of matter. Okay, so if you have a chunk of iron that has a certain mass of, say, 10 kilograms, that mass is always 10 kilograms no matter where it is in the universe. Okay, the mass of that body is 10 kilograms, which means its ability to resist motion will depend on that 10 kilograms of mass that it has on it. Okay, so it's the sum of the masses of all the protons and electrons that compose that body, right? So this concept of mass unifies the properties of all matter by just choosing this one, one aspect, namely mass resists any change in the state of motion, or mass gives you the acceleration. So the common confusion is that since we use sometimes similar units for mass and weight, we confuse mass and weight. But really, the units for weight are not kilograms, okay? The units for weights, you can say kilogram weight, but you're not supposed to use kilogram. In fact, the correct units for weight is newtons, okay? Named in honor, of course, of Newton. Now I'm going to give you examples of why mass is not equal to weight, all right? First of all, conceptually, weight is a different thing. Namely, weight is a force, okay? What is a force? What force are we talking about? So weight on Earth is the force with which Earth attracts the body of mass m. Okay, so the weight is the force. So if you have a body of mass m, we know that on Earth the acceleration is g of 9.8 meters per second squared. So once you multiply these two, then you get the weight of the body on Earth. And if you take this body to some other place, and where the acceleration g is different, okay, then the weight will be different. So that's why we say that objects are weightless in outer space, because you're circling the Earth and you sort of have zero weight, because the acceleration towards Earth downwards, the downward acceleration is zero, so we say it's weightless. So, if the units of mass are kilogram, then the unit of force or the unit of weight will be mass times acceleration, will be kilograms times meters over second squared. And that quantity, kilogram times meters over second squared, that complicated quantity is abbreviated by Newton. Okay, so that's the weight is 1 Newton, or the force is 1 Newton. So if we calculate the force of attraction of Earth on an object of mass 1 kilogram, so then we take mass is 1 kilogram, weight and acceleration is 9.8 meters per second squared. This should have been a superscript. And you multiply the two, then the weight is 9.8 newtons. Now, let's take the specific examples now. All right, so as I said before, a body of the same mass can have different weights. Even on Earth, the body of the same mass can have different weights. So if you want to lose weight, go to the equator. But you won't lose much weight. You'll lose just a little bit. I'll explain to you why. The reason that you are slightly less, you feel less weight namely there's less force of attraction that you feel when you're at the equator, is because the effective acceleration is different because the Earth is spinning. Yeah? And as we already explained, that the value of the acceleration here is g, and the value of acceleration here is less. And so we'll see how your weight on the moon also later on is less than your weight on the Earth. Now this is a big difference, okay? Because we'll see, according to the law of gravity, that the force that the moon exerts on your body is less than the force that the Earth exerts on your body. And similarly, the weight in an orbiting satellite can be 0, but the mass is the same, okay? So there you have this weightless experience because you're going around the Earth, and your value of acceleration, instead of going this way, you're going in a circle, and so you appear weightless. Now here on Earth, this part of the Earth is spinning more than up here. Your force on you is mass m times g minus this much, so you weigh slightly less at the equator. So it's a little bit of a fuzzy concept in the sense that this acceleration is really there. The full g is really there, but part of it is being used to spin you. Okay. All right. So that finishes the discussion of the mass. Now I want to show you how Newton went further from the idea of F equals ma. And by the way, this he used as the key to the mechanical universe, namely the key to understand the workings of the mechanical universe. Now, Newton used this key in two ways. Okay? The first way was if he knew the force and he knew the mass, then he could calculate the acceleration. Okay? And from the acceleration, you can deduce the motion. Okay, so if you know the force, you calculate the acceleration, and once you know the acceleration, then by using Galileo's laws, you can calculate velocity versus time, distance versus time, time taken to travel to a particular distance, or the period of oscillation of a pendulum. You can calculate all of that if you know the force and the mass. Okay, and these, for example, are your equations that you use to calculate from acceleration. Okay. Which we've discussed earlier in chapter 4. So now let me use a very, over here. I'll give you a very trivial example, okay? Suppose you know that the force is 0, okay? That's also, by the way, definition of something being in equilibrium. So now, if the force is 0, then according to this equation, acceleration is 0. And if the acceleration is 0, you can use this first equation to show you that if this part is 0, the velocity equals v initial, which means the velocity will stay constant. Or you can say this part is 0, and so distance traveled goes as velocity times time. Okay, because acceleration is 0. All right? So this is a very simple example of equilibrium. And by the way, if you're in equilibrium, you don't have to be at rest, right? You could be moving at a constant velocity. You're still in equilibrium. Now, the second method which Newton used to use this law F equals ma is, suppose he knew the motion, then from the motion he figured out the force. This was really his forte. Okay, this part was really his forte. So the way he figured out the law of gravity was by using this law F equals ma backwards to figure out the force. And I'll show you how he did that. Okay, so let's take this trivial example of this object on the table. Right? We already know, I'm going to try to make you think like Newton. Okay? We already know that it has a mass. Okay? Let's say it's got a mass of m. So because it's got a mass of m, the Earth attracts it with the force mg. And yet it doesn't move. So from its motion, can you deduce the existence of some other force? Why doesn't it move? Right? There's a force, the Earth's attracting it, right? Because if I put it over here, it will definitely fall, it will definitely move. But if I put it here, it stops moving. So what's happening? So you see, from this motion, namely the acceleration is 0, Newton said there must be another force acting on it. Okay? So he created the idea of another force that's acting on this object, and that force arises from the table. The table exerts a reaction force, sort of like my muscles exert a reaction force to prevent this from falling. Or if you had a spring, then the spring will stretch to prevent it from falling. Similarly, that you can consider all the atoms of the tables as little tiny little springs pushing up on it. Okay, it's actually very close to the truth, because the electromagnetic action of all these atoms provide a little tiny upward force to counteract this weight, and so the sum of all of that is called the reaction. Okay, the reaction force. So here you are, an example of how Newton used the motion, namely zero acceleration, to figure out the existence of a new force, namely the reaction force. So as a result, acceleration equals 0, net force on this object is 0, which means that this downward force of gravity's attraction is compensated by the reaction force, which is in the opposite direction, and so you get reaction equals minus F1.